Hi and welcome back. So I'm going to pick up here with some further revision on our mean and standard deviation. So the mean, we're pretty comfortable with that. We've been working that since we were in primary school. We take the sum of the numbers, so we add them all up and we divide by how many we have. And you know, because we're in science, we like to write things in a formal way instead of add things up and divide through by how many observations we have. We write the sum of the xi divided by n, where n is the sample size. Okay, it's just formalizing something that we've been working with for a long time. It's a similar situation with the standard deviation. What do we do when we want to find the standard deviation? Well, in practice, we can just go to Excel, use the stdev.s function, and we find the sample standard deviation. What's the formula? What does the formula say? It says find the difference of each value from the mean, take the square of that, add them all up, divide through by the sample size less 1, and then take the square root of that. Okay, so there's a few more steps involved, but we can kind of cope with it. It's not too bad. Let's just look at it in a bit more detail so we understand what's actually going on with our standard deviation formula. So the first thing is, why do we actually square this thing? So it seems that we square it and then take the square root of it. That seems to be making things unnecessarily complex. Well, what happens is, if we don't square things, if we just took the deviations without squaring anything, we would find that the differences would be 0. So what we do is we square them, and then because we've squared them, after we've worked on that, we take the square root of it to put things back on the same scale. So really all we're doing is, because of this problem, if we just looked at the deviations from the mean, they would all wash out. Some would be positive, some would be negative. And then the sum of those differences would be 0, and so that wouldn't give us a measure of spread. We square those terms, and then we undo that squaring with the square root sign. Now, the divide through by this n minus 1 bit, in practice, if you work through all of the calculations and you do all this and you do all of the substitutions and you get drilled in this, you'll find that yes, the formula drops out as n minus 1. And you can prove this, all right? And if you were taking a math course, you might prove it. I got a couple of observations on this. One, okay, so we just say that if we used n, it would understate the true variability, okay? That's all it means. But it's n minus 1. So as our samples get large, this issue goes away. So really, you start thinking about, you know, if I've got 20, if I'm dividing through by 20 or 20 or 21 or 50 and 49, it really doesn't make much difference. So as long as we've got relatively moderate sample sizes, the divide through by n minus 1 thing kind of doesn't make much difference. So rather than forcing you through all of the notation that can prove that it's n minus 1 rather than n, I just thought, well, let's not worry about it, okay? And move on with life and get on to the practical things like how we're going to use this measure of standard deviation. Rather than the formula, it is good to have an understanding of what's going on though. And so when will the standard deviation be large and when will the standard deviation be small? So if we look at this and we look at the numerator, you can see that if the values are widely spread around the mean, then the numerator is going to be large. And if the numerator is large, that means that the standard deviation metric is going to be large. If the values are quite closely clustered around the mean, it means that the numerator will be small. The deviations from the mean are small. So if the numerator is small, the whole expression is going to be small. And that's really the essence of this. So what is standard deviation telling us? It's telling us about the spread of the data. So what have I got here? 3 different samples, each with a standard deviation they all have the same mean of 8, each with a different standard deviation. So you can see as the standard deviation increases, the spread of the data increases. And that's all we need to know. So when the standard deviation is large, the spread of the data is large. When the standard deviation is small, the spread of the data is small. So why are we using this mean and standard deviation? Because if we have this rule, about 2/3 to 70% of the data is within 1 standard deviation, 95 is within 2 standard deviations, and we find that almost all of the observations are within 3 standard deviations. And it's traditional to add this information to a histogram. So really, when we're talking with symmetric distributions, and we will be working with symmetric distributions a lot, the mean and the standard deviation are very useful. I really do use histograms a lot in my research. So something that I've been working on is alcohol policy. This is an example of the distribution. It's quite skewed. So we have many people that don't drink a lot and a few people that drink quite a lot. And the reason that this, you can't really see them on the scale that I've got here, but there are some people in this distribution that drink a lot. So it's quite a skewed distribution. So if you look closely at the axes, you can see that initial group is about 45,000 males, and in the female group, it's about 75,000 females. So this is, I'm working with a relatively large data set here. I think there's about 400,000 observations in that entire data set. So it's a big data set. I've also been working on mining policy. So mining's quite important to Western Australia, and in particular, this interface between, do we support it? What are the environmental consequences? And so I was looking at some government policy, and this is some published research of mine, and I've taken just a screenshot of the paper, and I've measured this density is relative frequency. So rather than measuring it on the scale of units, I've put it on the relative frequency, and you can see here that I've added some lines. But again, very, very common thing to be working with. And again, I think in these plots there's 10,000 data points. So relatively large data sets that I've been working with here. So when to use a histogram? Well, we typically use a histogram when we want to get a single, when we have a single distribution that we want to summarize. That tends to be when it works best. I use it often to get a sense of the data, and if you're a student here at UWA, we work with these distributions when we look at the marks, and I've spent countless hours in Board of Examiners meetings and faculty teaching and learning meetings dealing with these kinds of distributions. So let's get a sense of what some of these distributions look like, what a basic histogram might look like. So with our symmetric histogram, here's something that I've got here. And you can see, like, okay, the mean is around 11 to 13, and it's a nice symmetric distribution. You might notice something about this plot. If you look carefully, you can see that I don't join the axes. This is one thing, because sometimes people think it's misleading. They think that the axes would start at 0, and because I start at 6, I've highlighted that by not joining it. So that's a little signal to the reader that yes, rather than have lots of white space on the page, I've gotten rid of that white space, but I'm trying to make sure that you're aware that the axis doesn't start at 0. Sometimes I like to start the axis at 0 and make it clear to people that we're some distance from the axis. So that's the same data set plotted, where it might be conventional to show the 0 point on the x-axis. And because I've joined my x and y axis here and they cross each other, I'm showing that space, and I'm making people aware of how far away I am from 0 with that plot. We can also end up with skewed distribution. So we might see I might have a long right tail. This is again something quite common that we see in our data. So that's sort of that alcohol consumption distribution I was looking at, but that was truncated at 0. We can have things being skewed the other way. We might have some low observations and much of the distribution sitting like this. Histograms can be really useful for highlighting features that you might not see when you just tabulate the data. So something that's bimodal. This can be common when we have different strains of a species, or males and females, or we're measuring something and they're systematically different, and we've just tabulated the data, and if we plot it all, we can see that those things break out. Plotting a histogram can be a good way to detect an outlier. So this is an example of something that's an outlier. Outliers are things that don't belong to the population that we're considering. And in this case, I would go and have a look at that data. It might be a data entry. It could be something that went wrong with my measurement equipment. I'd really want to investigate what was happening with a data point like that. So when we have a histogram, it can be a really good way to detect outliers. And outliers are things that don't belong to the population we're considering. In this case, I think it's pretty clear that we have an outlier, but in other cases it might not be so clear. So say we had a skewed distribution. If we have a skewed distribution, we can imagine that those observations are going to appear on the far right hand side of the tail. So I wouldn't be 100% certain that I had an outlier when I had a skewed distribution like this. But it's still something that we would go back and check. So a really important part of working with data is getting an understanding of your data before you do any analysis and checking it and saying, okay, yes, I'm 100% certain that the data is correct. And in this case, I'd still investigate, but I might have an outlier. The other thing that we can do with histograms is look at relative frequency. So this is what I've got here. You can see that rather than plot on the scale of counts, I've plotted it on relative frequency. And that's another really valid way. You tend to use relative frequently when, say, you've got two distributions that you want to compare and the number of observations in each group is different. And because the number of observations is different, then one would the larger plot would overwhelm the smaller plot when you put them on the same page. So you plot them as the relative distributions. So something that's not been made clear when we've been looking at these plots that I've put is how do we decide what the bin sizes were? So whether it's a relative frequency plot or a normal histogram, how do we create the histogram? We need to decide on the bin sizes. So the bins are the columns, right? How wide is each column that we put things on? And there are a number of decision rules here. So the classic ones I've listed here. They're named after people or their rules of thumb. So the square root rule of thumb. And these are, the fact that there are many decision rules tells you that there's no one correct rule. So this is going to be a theme that repeats itself. There's no one correct right answer or no one clear way to do something. But what we're going to have to do is learn judgment. And so that's really a difficult skill to learn. And so for a histogram, I think that the judgment is whether the bins are too wide, the plot looks a bit clunky, and when the bins are too thin, it looks too narrow. So let's have a look at how some of these decision rules work. And the first one we use Sturge's, which unsurprisingly, as we're trying to link things, has a link to using logs. So this Sturge's decision rule would say the number of bins. So the number of bins means the number of columns we would have in a plot. We find as log base 2 of the sample size. So say I had 100 observations, I would have 1 plus log base 2 of 100, which is 6.6, so 7.6, and usually we would round up. You don't have to round up, but the convention is usually to round up. So if I have 8 bins, so that tells me how many bins I would have. So I now need to look at my data and look at what the data range is. So say in this example, my data ranged from the lowest value was 1 and the highest value was 16. I would have the range of 15. So my bin width would be 2. So I want to have 8 bins, and with my 8 bins, I need to span the full range of my data. So I would end up with around a bin width of around 2. All right, and then you can obviously imagine that things fall on the border line of something. And so we have this notation, if you really wanted to look at this, of open and closed. So if we want to include one side, we use parentheses, and not the other end, we use brackets. So the way that we would have anything falling, so the way that we would split our number line is to have open and closed sets, and decide a priori which way we want to go. It doesn't matter, it just means that we can explain that if you fall on the borderline of a bin, you're in one bin or out on the other side. Another common one that we use is Scott's and the FD decision rule. So I've got those rules here, so they are functions of the data spread. So the bin width is some decision rule based on spread, one based on the variance, so that's variance standard deviation, and one based on the interquartile range. So variance is the one that goes with the mean, and interquartile range is called a robust measure. So different decision rules, and one that you used to apply in practice for your own self was the square root decision rule. And that's one that when I used to work in Excel, I probably used the square root decision rule because it was the simplest to implement, if I could speak. So what's my take-home message? There's no right or wrong number of bins to use in a histogram. You have to use judgment. What would be good for you to know is how do these different decision rules play out in practice, and I've got some examples here. So what I'm showing you is the way it works is basically I've ranked them with Sturges. You get, as the sample size increases, the number of bins that you have, or the number of columns in your histogram, grows relatively slowly. When you use Scott, it's in the middle, and when you use FD, the bins grow very rapidly. So which one you use depends on which one looks good. So I can show you this with a hypothetical example that I've just created here. So this is what it looks like when I apply the Sturges decision rule. This is what it looks like when I apply Scott, and this is what it looks like when I apply the FD decision rule. So I would actually say that the FD is starting to look ragged, and Sturges is looking too chunky. But what we do know is that about 2/3 of the data lies within one standard deviation of this, and about 95% of it lies within 2 standard deviations of the distribution. So what have we learnt here? So we've learnt that if you know the mean, you know the centre of the distribution. If you know the standard deviation, you know how spread out things are. And when we're looking to summarise a distribution, we use a histogram. And the correct histogram to use is not clear. It's something that we use judgment on, but we've got a couple of decision rules that we know about how to make the histogram look smooth, have more bins or less bins, and we're going to learn how to play around with that and how to create nice histograms. And that's an opportune point to stop.